Okay, so now we will start with the second problem. It is this. Let's have a look at first. So this question, it will be a little complicated. If you can remember, when we solved the past question, we only used the Bernoulli principle and mass conservation principle. In this case, actually, we need to use the energy equations. So you see here, water at 20 degrees centigrade temperature. It is pumped from a reservoir. You see the left hand side of this picture, and the flow rate is 120 liter per second. It is ideal flow. We need to calculate the distance x. You can see from this figure the x. We got the pump. Initially the diameter was uniform, and when actually the exit nozzle, the diameter, you see it reduces to 80 millimeter, but before that actually the pipe diameter, it was 160 millimeter. What we need to calculate initially is the distance x, where the cavitation is about to appear at the pump inlet. So I'll tell you that later. And we actually need to calculate the pump power. So you just have a look the picture here, the total drawing of this system, and we know this height is given 30 meter, and you can see this pipe creates angle with the horizontal axis. It is 30 degrees centigrade, 30 degree. So if we start with this problem, let me have a look here. What we can say, the diameter, actually, it is for the initial section, it is 160. For this outlet diameter, it is 80 millimeter. This distance is equal given 30 meter. It creates the 30 degree angle here. Okay, and what we can say that, okay, the height, actually, if I say, okay, that I will explain later. We actually initially we need to calculate the distance here where the cavitation starts. So the pump is here. You all know cavitations actually occurs when the liquid in a pump turns to a vapor, and when it becomes a vapor, it is at low pressure. So it occurs because there is not enough pressure at the suction end of the pipe of the pump, or you can say the net positive suction head, it is insufficient on that section. So when cavitation starts, occurs, air bubbles created at that section due to the low pressure. So in other words, we can say, when we will solve any problem like this, if it asks about calculate where the cavitation starts, so the pressure it will be here is the vapor pressure. Okay, maybe in week 2 or week 3 we discuss the vapor pressure, how it creates and what is vapor pressure. So we're not going to discuss this today. So for better understanding, what we can say, maybe let's say this reservoir at this end, or this pump inlet, the pipe inlet, let's say this is A. The pump, this section, let's say this end is I, and the exit section, let's say this is section E. It will help us to actually solve this problem. Alright, and the other informations are given. This height, the reservoir here is equal 10 meter, and we all know the other variables. So if I actually try to give you some more understanding, so look, we actually need to calculate this distance x, and this pipe, it creates a 30 degree angle here. If I want to calculate this height, because we need this height if we actually want to calculate that distance, so can I say it will be something like this? Maybe I can draw this section here like this. So let's say it creates a 30 degree angle here, and let's say it's something like this. This is actually this height, this one. If we denote like this way, A, B, C, so this distance actually from here to here, this distance, it is actually x. So we can say this is x, and we need this height. So we actually use the trigonometric functions for sine theta cos theta, and you know, when it creates a 30-degree angle like this, if we want to calculate this vertical edge, then actually we know the formula. It is, if I implement this triangle, so tan theta, it will be like the vertical axis is BC, and the horizontal on like AC. So here actually tan and theta equal 30-degree. BC, it is, let's say, the height we actually need, and AC, this is actually the x I showed you earlier. So this is x. So we can say this height, it is equal x tan 30. Okay, so that means we can say this is x tan 30. That's actually in this question it's mentioned that it creates a 30-degree angle. So this height, it is actually x tan 30. So the first part of this question is we want to calculate this distance where the cavitation starts at the pump. So if I start like this, what sort of information is given? If I write it down, so we know the barometric pressure. It is given 101.3 kPa. Okay, so this is given, and the height, it is given 10 meter. All right, so the pipe diameter is given 160 millimeter, and the nozzle diameter is given, it is given 80 millimeter. The S, that height for the nozzle section, is 30 meter, and theta is 30-degree. All right, so now we actually need to calculate the distance. The first part is the distance at this section. So what we don't know, guys, we don't know the velocity. Okay, we only know the flow rate. It is 120 liter per second. We know the flow rate at the pipe inlet section. So if we want to calculate the Bernoulli principle, we actually need the velocity for this section, like this A. So if we want to calculate you can ask me, okay, why you are doing this. So let me write it down at first. So if I use the Bernoulli principle, so from Bernoulli principle, at this section A and I, what we can write? We can write it is the pressure A, rho G, velocity A square, 2G, and let's say the height ZA. This is equal for it is section I. So PI, that means we said the pump is I. So rho G, this is BI square, 2G, and ZI. We define this way, this is I. So that means we actually need this velocity. Okay, so we will, as we know the mass flow rate for this section, so we can easily calculate the velocity from there. So the velocity for you can say the velocity for the pipe or the inlet section, it is the flow rate over the area. So the flow rate is 120 liter per second. So let's say it is 0.12 meter cube per second, and area is pi d square over 4. So this is 0.12, pi is 3.1416. Diameter for the pipe section, it is 160 millimeters, so 0.6 over 4. So it will be 5.97 meter per second. So let's say we say this is the velocity for the pipe section. Okay, we calculated this, the velocity for the pipe section. So once we know this velocity for the pipe section, then what we can do, we can easily implement the Bernoulli principle. So yeah, so now this is actually, you know, the velocity for the pipe section. And now what we will do, we will use the Bernoulli principle. So here actually the velocity we calculated, it is actually the velocity for the it is actually the pump velocity. Honestly speaking, it is pump velocity. Va, it is 0 because the water is at rest at this reservoir. So at this section the water velocity initially it was 0, and pump actually just sucking that waters. So the velocity actually we calculated, it is the velocity for this section, the pump Vi. It is actually Vi, and the Va, it will be actually 0 because the water is at rest at this reservoir. So the velocity at that section, it will be 0. So for better understanding, I can write it down for you. So let's say here velocity will be 0, okay, Va. And what will be the pressure? Pressure is given, the barometric pressure is 101.3, so we can say 101,300 Pascal. It was in kPa, we write it in Pascal. This height we can say from the Bernoulli principle, we said this is Zi for the pump section, so we can say Zi it is equal x 1030. Let's say Zi it is equal x 1030. We know G, we know the rho. Now what is the pressure? Za. It is 10 meter for section A. You will see here this is actually 10 meter Za. And now what else we need? We need the velocity for section I. We calculated it 5.97 Pascal, sorry, meter per second. So what else we need? We need the pressure at pump. It is actually the vapor pressure. I explained earlier. It is actually the vapor pressure because the cavitation starts in a liquid in a pump when it turns to a vapor at low pressure. So it will be the vapor pressure, and it is actually constant 2.34 kPa. Or you can multiply 1000s to convert it into Pascal. So now what we will do, guys, we will substitute all of these values into this Bernoulli principle here. So let's do that. So it will be something, the pressure A 101,300, 2 into the density for water is 1000, gravity 9.8, velocity term is 0, this height is 10, Pi is 2340, we just multiplied it, 2340 Pascal. Rho G, this is 1009.8. The velocity, the Vi squared over 2G, so it is 5.97 square over 2 into 9.8, and the height is x 10 30 degree. So if you clearly have a look here, you will see this expression is everything we know except the x. So if we solve this for x, then we will actually get the maximum distance where the cavitation will start. So it will be something like this. If we just solve it, it will be like this, like 18.3 over 1030. So x will be 31.7 meter. So that means this is the distance where the cavitation will start. Okay, so we got this distance where the cavitation is start. But the question, if you can remember the other section, it says you need to calculate the pump power. So now we actually need to use the energy equations. The pump power it is actually, the formula is we need the pump head. Okay, we need to calculate the pump head into the density, gravity, and the flow rate. So we know flow rate, we know density, we know gravity, so we need Hayes, the pump head. Okay, so the pump head we can get from energy equations. Okay, we can get it from the energy equation. So if we want to get this pump head, actually we discussed during when I discussed the theories, then I discussed this thing like the energy laws and the energy gain principles and the energy equations. So I'm not going to discuss everything now, but what we know the energy equation is like this. We will definitely implement the energy equations for this section A and section E, because this is the the inlet and this is the outlet, the exit. So it will be something like this. Let me write it down here. It is PA and rho G. Okay, PA rho G plus VA square 2G ZA height, and the pump head Hayes pump. I will explain. You all know already. PE rho G, PE square 2G, and ZE plus head loss. So here, guys, this term, it is actually the Hayes pump. It is the energy add. Okay, it is the energy add, and this is actually the energy loss. Okay, it is actually the energy loss. So for this system, we are having no energy loss, so we can use, so at the exit of the nozzle, we have no energy loss, so we can say this Hayes loss equals 0. And then we will have the expression like this. And if you see here, we already know the pressure A, and we know the velocity for section A, it is 0 because it is the reservoir. We know the height, we know the ZE, the height. Pressure at nozzle B, we know that. We actually don't know the exit velocity at the nozzle outlet. So what we can do is we need to calculate the velocity at the nozzle section. So here the best thing we can do is we can use the mass conservation principle. So from mass conservation principle, mass conservation principle. So from mass conservation principle, definitely we know the flow at section section A, it will be equal to the flow at section E. So what it is we can, okay, in this case, actually what we can do, we should use, if we want to calculate the velocity for section A, we can do the other thing. We can use the mass conservation principle, because the pump is started from here, so we can do it from this section I and section E. Okay, we can do it for section I and section E. Okay, yeah, that should be the appropriate one. Yes. So we can say the flow at section E, it will be equal to the flow at section I. So it is like this. If we calculate the flow rate at section E, it is BE, and the area, it is circular, so pi dE square over 4, the area, and it is velocity I, and pi dI square over 4. So what we can do here, we can just cancel out this term from the because it is an equation, we have the equal sign here, so we can easily eliminate that term. So it is VA, BE, and DE squared equal VI into DI square. So BE, it will be VI into di square over de square. All right, so bi, let me just write it down like this. The diameter, the nozzle section, the pump section, it is 160, so it is 160 square, and the exit section, it is 80 square. So that means it will be something like this. Be, it will be just 4vi, and we know bi, the velocity at the pumping light, it is this, so the velocity, it will be 23.88 meter per second. So this is actually the exit velocity. Okay, so we got the exit velocity. All right, so once we know the exit velocity and the exit distance, the height ze, it is given. If I go back, I think yeah, you see it is 30 meter. So that means we know everything. Okay, so we know everything. We can easily just cancel out this term here. If you look, the pressure at section A and section E, it is the absolute pressure which is given, and density, gravity, this is constant, so we can cancel out this term. Okay, because it will not affect the case, the overall results, because it is same, so we can cancel out. So now what we can write from this expression, it is something like this. Let's say va square 2g za plus the pump head equal b e square 2g z e. Okay, and we already have the energy losses, it is 0 here. All right, so now we can make this term 0 because at the reservoir velocity is 0. So that means this is 0. za, za, I think it is given 10. The pump head, yeah, be, the velocity, we just calculated 23.88 square, 2 into 9.8, and the jd, it is equal 30. Yes, so if we solve it for pump head, we will get it is 49.1 meter. So this is actually the pump head. Once we know the pump head, previously I calculated, I just write down the formula for pump power. So the pump power formula is the the pump head, density, gravity, and the flow rate. So you got it 49.1, density is 1000, gravity is 9.8, and it is the flow rate, if we consider into meter cube per second, so 0.12. So that means it is for 57,760 watt. So that actually that's the solution. The first part of this question is we had to calculate the maximum distance where this cavitation is stayed. The pressure will be the vapor pressure here, I explained already. And the second part, actually, we need to calculate the the pump power. So we'll discuss during the class, and I believe you understand this. Yeah, so that